Yo creo que
Okay, so I think we can start already. It's a pleasure for me to have as a guest today, Enrique Pérez Montero. We are long-time collaborators and friends, and Rocco as well, because he's an important part of the research team. Enrique did his PhD in Autónoma. Then he moved to Toulouse for a postdoc. And then you came back to Autónoma, or you were
no, to the IAA.
To the IAA,
Yeah.
where he works right now. So today he's going to talk about the last paper that we are about to publish. We are answering the referee these days, but the comments are not major. So the topic is, what can we learn on the hardness of the ionizing radiation from the nebular infrared lines? So yours, Enrique.
Okay.
Thank you very much.
Thank you, Juan Antonio. Thank you, one of you. It's for me too a real pleasure to be here today and share with you this part of the science we are developing, trying to use emission line, not just in the infrared, which is the paper Juan Antonio was talking about, but also in the optical. This is a long time project, and I want to share with you the results of it. As you may notice, I cannot see. So during this talk, I will use some resources based not just on the sense of sight, but the sense of hearing as well. In fact, I will give an outreach talk, 2 of them, in fact, tomorrow, based on these resources. But I also like to use them as a part of my scientific talks. So I hope you find it very appropriate. The first one,
interplay of stars, gas and dust.
It's try to motivate in which kind of context we are moving around, which is the interaction, the interplay between a source of ionization radiation, which can be a cluster of massive stars, an AGN or whatever, and the gas and dust around this cluster or source of ionization. Normally, to get the properties of this source of ionization is very difficult, because it emits radiation in very energetic ranges of the radiation, which includes X-ray, ultraviolet, that's mostly absorbed, obscured by the surrounding gas and dust. So we have the problem that we need to determine their properties just using the emission lines re-emitted by the surrounding gas, as the gas has absorbed the radiation and re-emitted in the optical as emission lines. As an example of this kind of objects, I have put there one, which is the 32 Nebula in the Large Magellanic Cloud. I cannot see that because it's blind, but I can hear that using this very beautiful result from the Chandra Observatory, which translates the infrared emission taken by JWST and X-ray into sounds using a sweeping that let me know which is the distribution of this gas radiation around the star cluster. I share it with you. one of the resources tomorrow in the university. This was the clickbait, and now I pass to more technical things about this work. I'm sorry.
Functional parameters.
The technical point is that we can define three main parameters that relate the gas, the properties of the gas and the emission lines, which is the field of radiation. All of them are very known. The main one is metallicity, the ratio of species helium and helium in relation to hydrogen. This is the chemical content of the gas. The second is the ionization parameter, which is basically the ratio between the number of ionizing photons in relation to the density of particles. And the third one is the hardness of the radiation, which can be parameterized, for instance, as a function of an effective equivalent temperature, assuming that it's a kind of black body. So this effective temperature gives us information about what is the relation between the long and the short wavelengths. If we, in theory, know these three parameters, we can reproduce any emission line. So we can do the opposite exercise, is to try to derive them from the emission line fluxes that we can derive in the optical, in the infrared, or wherever any spectral range.
Derivation of metallicity.
Metallicity is one of the main topics in my research during many years. I have not going to speak about that because I today want to focus on the hardness. And let me share with you that there is a code called HII-CHI-mistry I have been developing during the last 10 years. In fact, it was the first time here in the theater close to FEFCA in the SEA meeting 11 years ago, where I presented for the first time the first version of this code, which is able to reproduce the chemical abundances from a set of emission lines. And importantly, it is consistent with the direct method. There are a plot there comparing the results from the code with the direct method, which basically relies on the derivation of electron temperature. So we really think that it's a very accurate way to get abundances as compared with photoionization models.
What can we learn about the ionizing source?
About the nature of the ionization source, there are very widely known methods that maybe most of you know, that include, for instance, PPT diagrams, diagnostic diagrams, which relies on the relative emission line fluxes of some of them, for instance, oxygen 3, nitrogen 2, and there are in principle regions of the diagram which are expected to be ionized by the AGNs, or maybe shocks, or maybe star forming. But it is hard to know exactly what is the shape of the ionizing source beyond the fact that defining if they are AGNs or whatever. There are other methods, such as, for instance, to try to define the equivalent width of some certain recombination lines. So it is known that the flux of the line in relation to the continuum can give us any clue about the age of the stellar population, or directly to try to derive to find any spectral feature that we know that are related with the presence of a specific population of a star, such as, for instance, the world radial bands. Beyond that, it's difficult to know what is exactly the power of energy of these sources, including AGNs or star clusters.
Using emission line ratios for the ionization parameter and the hardness.
Among the most useful, widely used methods to try to do this are the ratios of fluxes of lines of consecutive states of ionization. For instance, oxygen 2 over oxygen 3, which all know that depends strongly on ionization parameter. But on the contrary, there are many authors that use the same parameter as a function of effective temperature, as a function of the hardness. There's a plot there by our friend Oli Dors using that. But this implies that you have first to fix ionization parameter. So this is, very inefficient process, because on one hand, if you want to know the ionization parameter, you have to take assumptions about what's the shape of the ionizing set. And on the contrary, if you want to get information about the shape of the ionizing set, you have to fix previously U. So it is basically on many assumptions that maybe or not are well established. Or beyond that, we know that the geometry of the gas, if there are a fraction of photons escaping from the nebula, this affects as well this ratio and others. They are brought there by Nakajima and Oichi, where they find that this ratio diminishes at larger resids. So they assume that probably at high redshift, the fraction of escaping photons is much larger. Okay.
Softness parameter.
So if we want to derive at the same time U and depth, we need other methods. This is one of the main one I want to talk about today, which is the softness parameter. It was already defined many years ago by our friend Pepe Vilche and Bernard Pagel. The softness parameter is not just on one ratio of two consecutive states of ionization based on lines, but in fact on two, oxygen plus over oxygen 2 plus, and sulfur plus over sulfur 2 plus. All of them can be measured in the optical part of the spectrum or the near infrared as well. And it is thought that this relation dilutes the dependence on U and metallicity and gives us a clue directly on the effective temperature.
Softness diagram.
If we represent this in four of the corresponding emission lines, oxygen 2 over oxygen 3 in one axis, and sulfur 2, sulfur 3 in the other one, we can represent not just the softness parameter, but the softness diagram, in which the softness parameter would correspond to the straight lines of the slope 1 in such a way that the points with a lower eta, the lower parameter, would have in principle a harder field of radiation, as we can see in that deployment that we did many years ago, for instance, H2 galaxies or circumnuclear star-forming regions that are in the lower right part of the diagram corresponding to a harder radiation field.
Models in the plane.
This, I have not listened.
Models in the plane.
The models, yes. As compared with photoionization models with one single star, that gives us the opportunity to compare it with a scale of the effective temperature. This confirms this trend. So in principle, we can use this diagram in the optical to try to derive the field of radiation, but with some problems. For instance,
Mars observations.
This is one example of one paper we made in collaboration with Mónica Rulaño using PMAS observation of a giant H2 region in M33, which is NGC 595. And this allows us to make models with a spatial distribution, so we could derive and to predict the behavior of the interparameter as a function of the distance to the center of the nebula. As expected, we should expect that the field of radiation is the same of the nebula because the cluster is the same, around 40,000 Kelvin, although it is a cluster. But when we compare that with models,
radial eta variation.
We see that this eta parameter softness varies even though the source of radiation is the same. Why? Because when we represent this parameter as a function of the emission lines, it depends as well on ionization. So it is not totally released from the fact that there is dependence on other functional parameter. And if we want to know exactly what's the equivalent effective temperature, we need to make another kind of approach.
Galactic eta variations.
At the same time, when we represent the variation of this softness parameter as a function of the radial galactocentric distance in sun-spiral galaxies, we see that there is a systematic effect that there is the parameter is higher when we move towards higher galactocentric distances. That could be interpreted in terms that the radiation field is harder at larger galactocentric distances. If you remember the previous plots, eta is lower when the equivalent temperature is higher. But we can answer to what extent this effect is due to a real variation of the hardness as a function of what, and to what extent this depends on other things, such as, for instance, the ionization parameter. Okay, this is the reason why
grid of models.
We calculated a very large grid of models, trying to cover as many of the functional parameters that we could in order to compare with the emission lines. This implies calculating models with values of effective temperature in using the WM basic atmosphere, covering a range from around 25,000 up to 60,000 Kelvin, covering a wide range and ionization parameter, in order to try to use these models to get the real variation between ionization and the hardness.
Metallicity dependence.
And it is important to say as well that there are other dependencies, such as, for instance, metallicity. Metallicity also contributes to the dispersion in eta parameter. So if we want to use these models, we have to take into account as well this metallicity in the grid of models. So basically, we have a three-dimensional grid of models varying on U, on TEF, and Z, the metallicity, exactly the three main parameters I talk about at the beginning of the talk.
H2-chemistry test code.
And then we designed a new version for the H2-chemistry code that I described very briefly, which the way it is working. Basically, it does not find the best model for which we can reproduce the emission-lines, but we used the emission-line ratios that we know that depend on the parameters that we want to derive. In this case, oxygen 2 over oxygen 3 and sulfur 2 over sulfur 3, the two main ratios that we were using in the softness diagram. And we finally calculate a weighted chi-square distribution from which we can calculate both the mean value, which is the most probable, and the uncertainty. This represents an advantage of other Bayesian methods that only gives you the best solution, but doesn't give you what's the uncertainty, how probable the all other models gives you the solution. This is the same method we use for metallicity at the beginning, which is consistent with the direct method, and we know that gives you as well the effective temperature at the ionization parameter. Let me say that these all codes are all public in the H2-chemistry webpage and the corresponding GitHub page.
101.
We checked that in a paper we wrote some years ago to some of the spiral galaxies that are better represented with data from Chaos, for instance. This is one M101, and when we transform the variation of eta into a TF, we demonstrate that effectively, indeed, the radial gradient of the eta is due to a radial gradient of the hardness of the field radiation. And this correlates with metallicity. It is stated in many papers that there is a relation between ionization and metallicity, but when we find only this when we fix the shape of the ionization radiation. When we release this and we use a wide range in our models, we find that indeed what we find is a variation of TEF with metallicity and not with U. As I not the plot, I think that it represents this variation, but let me convert it into sound. This would be the second sound of the talk, using a code that is called Astrofísica, in which I have represented time as the radius normalized to the effective radius in this galaxy, and the frequency of the sound is the effective temperature. As we move towards larger effective distances, we can hear, not just see. We are all seeing that plot, but not me. But I can hear as well how this represents really a variation of the hardness of the radiation in this galaxy. I know that it looks like a classroom of very young people playing the flute, but listening the frequency, we clearly see that there is a hardening of the radiation. Other two examples of this application.
274.
In the same case in which the gradient in metallicity is transformed, not transformed, but is correlated with gradient of the hardness of the radiation, not with U. And this one at 51.
51.
In which it's a gradient basically flat. This is a weird case, but this is suffering emerging with a smaller galaxy, and at the same time, the gradient of hardness does not appear because basically, probably it depends on the gradient of metallicity. Okay.
Importance of geometry.
Things are not so easy. There are many obstacles, and when we apply this to other samples of objects, this was chaos in which we can take data from individual regions, a very high spatial coverage. But when we apply to other samples, for instance, in manga, in one we have more than 200,000 H2 regions with data in oxygen 2, oxygen 3, sulfur 2, sulfur 3. We have a problem. As you can see there, many of the H2 regions on the sample, more than one half of them, lies in a region which would correspond to a set hotter than the hottest massive star, which is around 60,000 Kelvin. This has been interpreted by many authors that probably the component dominating the spectrum, the ionizing component there, are holes, which is evolved objects after or in a later stage evolutionary part of the evolution, which is hotter than what we expect. Sorry, I want to think. Okay, but and when we apply the code using not just massive star but raw models that correspond to planetary nebulae, which effective temperature of the order of 80,000, 100,000, 120,000, which is really, really hot, we are able to reproduce this diagram using that temperature. But we can verify that when we replace the sulfur 2, which is confirmed that is affected by a large amount of thick diffuse ionized gas emission from the other parts of galaxy, even in the same region, but each one of these spaxels is around 1 arcseconds or so, which is very contaminated with, no, it's more than 2 arcseconds, in fact, I think. Very contaminated. When we replace this line with other low excitation lines, most of the sample, again, lie in the spectral region. So we have to be very careful when we're using this kind of diagrams. If we suspect that there are contamination from other parts of the diagram. Why am I telling you this? Because we will see that there are other versions of the same diagram that we can use in order to avoid this contamination, because if not, we are probably going to get a very unusual value of this effective temperature, even if the method is well calibrated.
Escape fraction from helium-2 emitters.
Another factor that affects this diagram is, as we saw before with the plot by Nakajima, is that many of these ratios are also affected by a probable fraction of escaping photons. So we calculated as well what's the effect in those galaxies which present a nebular emission of helium-2. And we know that they are not AGNs. There are many, not many, there are around I remember 90 or so of them in all Sloan catalog, which are not AGNs. So it's interesting to know to what extent, what is the nature of the stellar population ionizing these galaxies with helium-2 emission, which is not associated to overhead star because it's narrow emission, and to see to what extent a fraction of the photon escaping of these galaxies. You see there a grid of models for different values of the absorption factor, which I think lies above all at the right of the diagram. And when we are cutting the model to represent different versions of the matter-bounded geometry, we move to the left, and most of the models lie in a region that is only compatible with a non-negligible fraction of escaping photons. But one important additional factor is what is the metallicity you are assuming for the star. For instance, when you change the spectral energy distribution of the models.
Models with very low metallicity.
At the lowest allowed metallicity in the bypass libraries, we see that the models move towards the left. I really hope that you are seeing this in the screen. I confident that this is what you see in the plots. Okay, so the escape fraction that you derive is slightly reduced, even though when you are assuming
models with pop-free stars,
metal-free stars, which are basically population 3, more or less black bodies with temperatures of 100,000 Kelvin or so, this fraction is reduced, but you always find that at least 20–30% of the photons escape, even assuming the most optimal consideration about the metallicity of the stars. So this diagram can be used as well to try to know what is the fraction of escaping fraction of to know what is the metallicity of the star. So if we have
analyzing deep optical observations of green peas.
If we have a sample objects for which we already know the fraction of escaping photons, this is, for instance, what we have here. This is a sample of green pea galaxies. Green pea galaxies, I don't know if you are familiar with, that basically very compact star-forming galaxies, and undergoing vast of star formation. If you measure in the ultraviolet the Lyman continuum, you can get an estimate of the number of escaping photons. So we can make the opposite exercise, which is to try to get what is the metallicity of the stars, knowing in the models what fraction of photons have escaped. And as we compare with the observation from X-shooter, that in an angular fraction of a green piece, you need to assume that the metallicity of the star is much lower than the metallicity of the stars if you want to match what's the fraction of escaping photons. So this kind of diagrams can be used not just to get the number of ionizing photons, but to try to know, as at the beginning of the talk, what's the nature of the ionization source.
Application to spatially resolved helium-2 emitters.
This is another example of paper we are preparing in Granada about Muse observations of SBS 0335, which is a compact H2 galaxy with a very, very, very low metallicity, for which we have detected a region of the galaxy with helium-2 nebular emission, and we can easily see that the only way to match the number of predicted escaping photons in the region with helium-2 in relation with the region without helium-2 is assuming that the metallicity of the stars is even lower. So could be in principle be consistent with the fact that probably they are very, very, very metal poor stars that are ionizing the gas, and as a consequence, we see this helium-2 emission. Just using diagnostic diagrams based on emission lines without seeing the ultraviolet. Okay.
Stefan Quintet.
Let's pass to infrared. Another cookie for you of sound. This is an image of the Stefan Quintet as seen by James Webb. We will hear a sweeping of the entire image, and this Stefan Quintet is relevant for the rest of the talk because firstly it's infrared, and because some of the galaxies involved in this interaction are also AGN. So this is a Stefan Quintet not just seen but also in sound. So the question is, why looking at infrared can be important? What can infrared offers to us in relation to I have just explained to you with optical lines? Well, the first one is evident in the case of these galaxies, for instance. The fact that infrared can penetrate much more efficiently in the dust can allow us to analyze regions that were later obscured by the dust and cannot be seen in the optical. Second thing is that they do not depend as much metallicity as collisional emission lines in the optical can do. So this dependence is much lower. And third, and more importantly, the amount of data as seen with infrared in the last year have become much, much larger. So we have a statistical basis to try to check to what extent diagnostics based on the infrared lines, I'm talking about mid-infrared as a whole, can be used. Of course, we are not at the level of surveys like MANGA or DESI, which involves millions of points. But in the next year, we must be prepared to try to have this kind of diagnostic in order to analyze data. There could be another talk based just on the duration of abundances, but as I'm focusing today in the hardness, I'm going to see what results we have obtained. Firstly,
the infrared softness parameter.
We can define an alternative infrared softness with the same philosophy, which means two emission-line ratios, one of them covering one redshift energy, for instance, neon 2 at 12 microns, more or less, neon 3 at 15 microns, in relation to the ratio of sulfur 3 at 18, also at 33 microns, and sulfur 4 at 10 microns. For me, it's incredible because 10 years ago, for me, it could be totally impossible to know in memory the wavelength of the light in the infrared. But working with that makes miracles, of course. Okay, it could be the new infrared softness, and this is the behavior.
The infrared softness diagram.
In the plane as compared with models. This is the version of the paper we did many years ago, just analyzing the softness diagram in the infrared and the collection of objects already observed there, many of them, most of them observed with a spectral. And as compared with models, again, we can see that there is a double dependence on the effective temperature and on the ionization parameter.
Sampling new infrared data with IDS.
But we are now lucky and we have more and more data to repeat this analysis thanks to databases such as, for instance, IDS that has been partly developed here by Hernán, for instance. I thanked him yesterday for that, because we have now not at the order of thousands, but already hundreds of objects for which we can get this kind of analysis. We have made already a couple of papers related with chemical abundances, and this one is related with the hardness.
Dependence of the diagram on models.
This is the relation of this the kind of observations in the same 2D diagram, softness diagram, as compared with the models we have calculated. And one of the things that we see is that the slopes of the different evolutionary tracks is not one. So again, we cannot use just the parameter to get the hardness, but to need another kind of tool like HII-CHI-mistry if we want to break the linearity of the dependence between TEF and U. The good news in the infrared is that
dependence on geometry.
The dependence on geometry, which means to cut the model and let many of the photons to escape, is not as high as in the case of optical, because this is involving lines with are of higher excitation. So letting some of the photons to escape from the line is not so relevant. And
dependence on dust to gas ratio.
Dust to gas ratio does not alter neither the relation of the model. So this is another free parameter that gives us more information about the results.
Applying the HCM code.
So we have defined an alternative version of the code based on just on infrared lines, just using this line I have defined before.
Relation of the effective temperature with metallicity.
And you see there which are the results for this IDS sample as compared with metallicity. There is an important thing to state here. But there's another thing before I have not commented.
Applying the HCM code.
I think you can see your leaves there. Is correct?
Yeah.
Are your leaves in the plot there or not yet? Or not there? Or not yet?
There are so the histograms of effective temperature and log U.
But for your leaves as well.
For the U leaves, yes.
Okay.
The U leaves are in green.
Yeah, because there was something I wanted to comment. There were a couple of things that are important. First of all, you cannot see there any of the object lying in a range of ionization radiation hotter than the maximum considered effective temperature. And this is important because it implies that if we are using lines of higher excitation, they are not contaminating by Dick. If the main source of ionization in this sample were Holmes, you could see a hotter temperature even using the highest ionization state, but you don't see that. So this confirms that probably in the case of optical, in the case of manga observation in which you have a very low spatial resolution, is contaminated, but sources different for the ones that you are considering in the same spatial position. And the second one is that the effective temperature is not very different for different families of objects, such as, for instance, ULIRCs, ultra-luminous infrared galaxies. It has been claimed in several places in the literature that it is expected that ULIRCs have a hottest source of radiation, but when we use this diagram, we don't see a variation between the hardness in ULIRCs and the rest of the sample. And the second difference
relation of the effective temperature with metallicity
is the relation with metallicity. As we see before, we saw before for the case of galaxy disk, it was a relation with metallicity in the sense that there's a gradient of the hardness in some galaxies presenting a centennial gradient in metallicity. This is already seen more or less for the star forming, but not for ULIRCs. This is very, very curious because ULIRCs presents more or less the same effective temperature. There are some of them with very low metallicity. There are 4 of them there that which present at the same time more or less the same expected effective temperature of the order around 40 and 50,000 Kelvin. Let me stop a bit on this for objects. This is very important.
Deep diving objects.
Because we have published a paper written by Borja Pérez Díaz, my student, and a student by Pepe as well, on nature astronomy, in which we analyze what's happening with this with these 4 ULICs with very low metallicity. First of all, let us think that the method that we use to derive metallicities confirm that most of them lies in the mass metallicity relation in a region around solar metallicity, contrary to other recipes that predicted that most all ULICs had metallicity other than 2 or 3 solars. No, this is not true. When you assume a relation between N and O, you derive the correct mass metallicity relation, with the exception of 4 there that are extremely metal poor. There are some of the images of the HST there of these 4 objects, for which what we think is happening is that, well, when you get the nitrogen abundance in these same galaxies, this is not very low, but in fact, on the contrary, the nitrogen are of the same order that we could expect for the same mass nitrogen relation. But the difference is only with oxygen. What's happening there? What we think is happening is an inflow of metal poor gas that has 2 consequences. One of them is it's reducing the overall metal content of the galaxy, and it's boosting the star formation of the galaxies. To confirm this, we see that the relation between the number of objects suffering this process, this metal influence probably due to the merging process they are undergoing, as we can see in the images, and it's very quick. So this is what we have called a deep diving in the mass metal relation, because the galaxy lowers their metallicity very quickly, and as soon as they recover the metal content, because stars are ejecting again and again the models, they recover to the mass metal relation. So in the context of my talk, this would be that even in these cases, the hardness of the radiation, the equivalent effective temperature in these galaxies, is not different, and they do not depend on metallicity, because metallicity probably is driven by other processes different than the ones that is controlling the canonical chemical evolution of galaxies. Okay.
The softness valid for AGN.
And the last part of the talk is devoted to the paper we are reviewing with Juan Antonio these days here in FEFCA, which is the application of the softness, not just for star forming, but for AGNs. As you can see, it does not work at all. Using neon 2, neon 3 over sulfur 3, sulfur 4 as a function of alpha O x, this parameter basically parameterizes the shape of the shape in a double peak AGN. So a higher alpha value, around -1 or so, is harder than the one at -2. It does not correlate. Why not? Because these lines involve energies that are not typical of the set we want to trace. So if we want to use this kind of diagnostic, we need to involve other lines, and this is the advantage of the infrared, that we can find them there. For instance,
in new high excitation lines,
we can use neon 5 that can be observed at 14 and 24 microns. We can use oxygen 4 that we can be observed at 26 microns, and designing and creating ratios adapting to this shape of the set. We see there that now we can use this new eta parameter as a function both of U and alpha, which traces the shape of the set in AGNs.
Compiling a sample of AGN in the infrared.
Again, we have ideas to check the validity of our method. In this case, we have selected AGNs in IDEOS, but not just in IDEOS. There are the previous paper by Juan Antonio, Luigi Spinoglio, that uses not just lines in the mid-infrared with the Spitzer, but also using SOFIA, the far infrared, such as, for instance, nitrogen 3, the oxygen 3 line that can only be observed using this in this region. So we cannot, in principle, use IDEOS to define this parameter based on oxygen 3. And we confirm the AGN nature using, for instance, indicators such as, for instance, the equivalent width of the PAH that gives us when this is destroyed, is indicative of the presence of a very hard radiation field owing to AGN.
Arriving abundances in the sample.
In this case, deriving abundances is not so crucial because the softness in infrared does not depend on metallicity. but we already derived them in previous papers using additional recipes of the infrared lines for AGN. This is one paper read as well by Borja. I wanted to show this plot because it demonstrates that the range of metallicity in AGNs is not as narrow as we expected, only covering a weight range for over solar metallicities, but in fact we can find many of AGNs having half solar metallicity, even lower. Okay. Oops.
Arriving abundances in the sample.
This one.
Comparison of observations and models.
Okay, this would be the comparison of the sample of objects observed with SOFIA, which it implies involving oxygen through line with the models, for which we can see that even though the grid of models does not cover entirely the sample, we could in principle use them to try to get, I guess, for alpha and at the same time for U. We have, as I have just said, a disadvantage in the fact that we need oxygen through line. So an alternative
placing the O3 line
is to replace the oxygen through line and trying to search for alternatives based only on sulfur 3 and sulfur 4. So this would be the definitive shape of the parameter that allows us to analyze that in a larger sample of AGNs in IDEOs, and above all opens the gate to use the same parameter in JWST because it covers at least in the rest frame at redshift 0, because if you want to highlight the redshift, probably the oxygen 4 line is going to get out of the observed range. But we can use this diagram to try to get alpha in this very wide range of AGNs.
Models with different geometry.
As an important comparison, when contrary to the one with star forming, it depends strongly on geometry. When you change the geometry, I have changed the difference between this plot and the previous one is that in the point in which you cut the models, these are radiation bounded. So you are cutting the model when you consider that there are 2% of free electrons. The previous ones was with 98%. Basically, the previous one was matter bounded. This is radiation bounded. It is much more difficult to cover the sample. So this could be implying that in AGNs, most of the photons are also escaping from the nebula, and we should use the models assuming matter bounded geometry to get alpha.
Bimodal hardness for AGN.
An impressive result is that when you compare the distribution of the eta, new eta parameter for AGNs, it implies for ideal sample sulfur 3, sulfur 4 over oxygen 4, and neon 2, neon 3 over neon 5, we get a very clear bimodal distribution for alpha. We have made some statistical tests to confirm this. So it could be in principle confirm that there are two main modes of radiation field in AGNs with two different values of alpha. But we have the same problem as we had before with the eta for star-forming galaxies, as we have seen that in the plane we have two different dependencies, one for alpha and the other one for the ionization parameter. So this bimodal distribution, does it correspond to the hardness or to the excitation? Well,
breaking degeneracies with H2-chemistry.
Fortunately, we have a very efficient tool like H2-chemistry to feed it using just the emission-line ratios and to get the distribution both for alpha and for U. And this is the result, and this is up to some extent a bit surprising, because we retrieve the bimodal distribution for the two variables, both for alpha and for U, but with an anticorrelation. In such a way, there are two main families of objects, one of them with a hard field of radiation, but showing at the same time a low excitation of the gas, and the other one with a soft field of radiation with value of alpha around minus 1.7 or so, with a high excitation. Let me play with the sounds again, okay? Because I didn't believe very well the results that the code told to me. So I have sonified the distributions to see to what extent they correlate very clearly. So this one first represents the variation of alpha for this sample with the number of edges represented by frequency. It would be something like this. There are two peaks in the distribution. The second one is a bit larger. And when we put the other distribution in the axis of ionization, but going from higher values to lower ones, they match very, very clearly. So it demonstrates that there are an excellent correlation between all of them. This could be like something like this. They look the same, but when I checked that because I couldn't believe that. No, it's the same distribution. No. They correspond to one of the x-axis for alpha and the other one for y in the u. So it's really strange, but you would expect that the harder the field of radiation would correspond to a higher excitation, and on the contrary. So this is a very, very interesting result.
How do we interpret this?
And how do we interpret this? Okay, because it was already known that for some kind of galaxies, such as for instance liners, there are low excitation, and it was already known that the radiation field for the AGNs is harder. And it was interpreted in terms that, for instance, the density was different, or shocks were altering the emission-line intensity of the low excitation lines. But what we are observing that is there a very tight relation with the nature of the ionizing source, and they correlate. So why of that? Our interpretation, I asked ChatGPT to create an image trying to let me explain that. So that image you see there is from ChatGPT. I'm sorry for that. Juan Antonio told me before that it was okay. So it's validated, I think.
To a certain degree.
To a certain degree, okay. Why of that? Because our interpretation is that the geometry of the gas change as a function of the shape of the set. When the alpha is very high, it's because the efficiency in the accretion disk of the supermassive black hole is not very efficient. Okay, this change occurs very rapidly, and this implies that the number of very energetic photons is enhancing this, increasing very, very quickly. What happens if the distribution of gas around the supermassive black holes has a radiation boundary geometry, but the cross section of the gas is reduced when the energy of the photons increases. So many of them that were absorbed before, when their energy increases, they escape from the nebula. So when you convert a radiation boundary geometry into a matter boundary one, the low excitation ones are reducing, and this is interpreted as this is interpreted as an enhancement of the excitation of the gas. Okay, so this is what we interpreted is happening here. A change in the hardness implies that most of the photons are escaping, and this reduces the ionization parameter. On the contrary, when the efficiency of the accretion disk is efficient, this implies that the alpha is lower, and most of the photons are absorbed by the surrounding gas, implying that the ionization parameter is high. Okay, this is confirmed by the fact that there is some correlation between the two families that we have derived, one of them with hard softness, high field with low excitation, the other one with soft radiation, high excitation, with the different optical types of AGNs that we see. So the first one with soft radiation would be more typical in simple ones. The other one with a hard radiation field, low excitation, will be more typical for liners. Okay.
Fast transition in the hysteresis cycle.
To illustrate how fast can be changed the accretion efficiency in a disk of matter around the black hole, I share with this certification made by Juan Antonio, a game that we designed a couple of years ago. This is not for AGN, this is for X-ray binaries, GX339, in which we are going to see, we are going to hear how the ratio between hard and soft X-ray changes. At the same time, this implies that the brightness of the radiation field is reducing. So basically, it implies that when it's higher, the efficiency is lower. And in fact, we see that as well, that there is a vibrato representing the uncertainty that corresponds to a radio jet is activating at the same time. So let me share with you this video. It's 45. Maybe Juan Antonio wants to add something later, but I think it illustrates very well because it evolves very quickly from one stage from one another. This is the reason why we are seeing at the same time 2 bimodal distribution with almost no objects in the middle, and why at the same time it correlates with the properties of the excitation of the gas. This is the sonification. It is cool. This is based on real data, by the way. This is an outburst of this X-ray battery that was held in 2007. There were another 2 outbursts, but they are very irregular because it depends on the flow of material coming from the other stuff. So we have to refine that, and we want to make an animation of that, but I think it represents very well this case I have just explained about. That is the evolution of one state of the accretion disk, even for AGNs. So this is all. I think many things. I'm sorry, it was a bit dense talk, but I have tried to make it more easy to follow using sonification. Basically, you cannot use just one parameter to get the softness or the hardness based on the optical. You need models and a tool that allows you to discriminate the dependence on effective temperature ionization. This works for in the optical when you have enough spatial resolution. But if you want to get deeper, and you need infrared, infrared works very fine because it does not has any dependence on leak or metallicity, on dust to gas ratio. And above all, we can take some very high precision lines that allows us to open the game and to try to inspect spectral distribution with even higher energy. And when we do that, we obtain very, to some extent, an expected conclusion in the sense that there is correlation, anti-correlation between excitation and the hardness, even without seeing at X-rays. So I think this is a very solid conclusion. I shut up. I have talked a lot, so the only thing is to thank you for the attention and thank you. That's all.
Thank you very much, Enrique. Very nice talk. Questions? Don't be shy.
Even about the sounds, no problem.
They are still shocked.
Yes.
Audience?
You want to comment something on the last one certification?
Yeah, I can comment a bit on that one. So what you heard basically, can you go back to the figure?
Yeah.
Fast transition in the hysteresis cycle.
Yeah.
So what you see in that part is when the jet dominates. So on the right part of the diagram is the system is dominated by the jet, and the disk does not arrive to the last, to the innermost stable orbit around the contact object. And then as the system moves to the left, the disk, the dominance becomes higher, the jet disappears, and then the accretion disk comes to the innermost orbit. So the variation that you heard in the sound, like the larger amplitude wobbling that was hearing here compared to the high pitch wobbling, can be interpreted as the velocity of the material in the innermost orbit. So just to add an extra layer on that.
So, for example, in this kind of sonifications is the word, right? So, I suppose you use 2 variables for the sound, pitch and volume?
I'm using 3 in this case.
Yes.
So there is pitch, intensity of the sound, and then vibrato, the amplitude of the vibrato. So with these 3 things, you can play.
It is planned to use another one, an extra one, simulating the radio emission from the jet. In that case, we would use a different timbre. As in the case I represented the two distribution, one timbre for one variable, another one for the other one. In this case, the extra timbre, we have to decide which one will represent the radio emission at the same time. And will be overlapped in the phase where the efficiency is not high.
So I take a sample, a sound sample from a node, I do the Fourier decomposition, I take the main frequencies, and with that, I create a node with the frequency, with the main frequency that I want, and then I play with the rest of the variables, with the intensity and the vibrato.
And we could even simulate another one, which is, if we assume a gas distribution around, which is more or less excited as a function of the efficiency of the disk.
Exactly.
As an idea. You can add more and more variables, but probably at the end it would be like a crazy orchestra. So you cannot get anything from that, probably.
Normally you have to focus on one thing that you want to show. In this case, I wanted to show that there are 2 clear differentiated states. So I try to play with the variables to enhance that difference.
Yeah, this is like 3D diagrams from which I remember I couldn't see anything from that. Projected into a 2D page. Yeah.
Carlos, a question?
Yeah.
Thank you very much for the nice talk, Enrique. So in this diagram that you present, in which we have the alpha and the
Log U,
it's a clear. There are 2 clear blocks, as you say, and there is a diagonal, so there are things between. But there is also like an amount of sources that are like with an offset, or same alpha and log U. So that was the thing. So there are different kind of objects.
Is the one here?
He's asking about the liners. Yeah, is this diagram? So he's asking about the liners and also a number of Seyfert-2s that are at log U. But
there are very few, if I remember well.
Yeah, there are few compared with the rest of the sample, but they are clearly offset from the other sequence.
But we of course we expect that some of them are between the 2 distribution. But this is like the deep dive in Ulysses. The fraction of them are scarce, so this represents something related with time. This is a very quick evolution between one state and one another. If the time evolution between the 2 states is not as fast, we could expect to find many more of these objects in the transition region, but they are very few. So probably the transition is very quick, as in the hysteresis cycle. The surprising thing is that we see this fast transition also in U, because U is a property of the gas, not of the ionizing source. So this is the reason why we expect that there is something with the escape fraction of photons, because photons, go at the light velocity. So this information transmits very quickly to the gas. This is not something related with shocks. It depends on the velocity of the particles, or with the density, which is not going to change as abruptly as in the case of the change in the efficiency of the radiation disk. But the fact that they are very few probably underlines that this is very quick. But these objects will be very interesting to be studied, probably.
In this diagram, there are 2 states. No, one that we believe is dominated by the accretion disk, the other one that we think is dominated by jet or non-thermal continuum. But in theory, the objects should travel with time between the 2 places, but we don't know which track they follow. So it is interesting that there's a group of sources like liners that doesn't follow the diagonal, and they all fall separated from there. So that would be a nice thing to explore.
Yeah.
Nice, thank you.
Antonio?
Yep. So thanks, Enrique, for the talk. Very nice. I had a question about what is the impact of actually not being able to resolve the URI in the spectroscopy? I mean, they are very complicated systems and they have a lot of things going on, but your spectrum is the integrated spectrum, and the lines that you measure are integrated for the whole galaxy. So Do you think that this modality is still going to be there when you use JWST spectra for particular regions, or is just an effect of having all together?
Yeah. When you are dealing with adaptation lines in infrared, and you know that the source of excitation of this high excitation line is the black hole, probably spatial resolution is not so relevant, because although you get more than 1 AGNs in the same region, this is one of the other advantages as related with the excitation line or with the optical, in which you are integrating many things coming from different things, just in the case of manga for sulfur 2, you don't know what is the exact origin. But even though you don't have very high spatial resolution for infrared and you did a study in AGNs, you are up to some extent assuming very certainly that they are coming from the same point. So my guess, obviously we have to confirm that, but my guess is that you are not going to get different results when we are obtaining using a spatial data.
So these infrared AGNs are selected for having lower equivalent within the PAH than a certain value.
Okay.
And they systematically have high neon 5 to neon 2 or so they are AGN dominated.
Even in the low ionization lines, the AGN completely dominates.
Yes, because one of the conditions is that we have to have neon 5 and oxygen 4. If not, you cannot use this diagram.
Okay.
And this has to be concentrated.
Okay.
More questions? Okay, if not, thanks again, Enrique.
Thank you. Yes, I hope to see many downloads of HII-CHI-mistry in the next weeks.
From this IP, no?
Yes. Thank you.
Okay, you're dismissed.